Alright, hi guys. Sorry this is so long in coming. It took a while to try and troubleshoot the camera and figure out how I was going to upload all this stuff, but I think I've got it figured out now, so we should be good to go. I appreciate those of you that responded. I think I heard back from most of you that this is going to work out okay, at least on your end, so hopefully I've got the tech worked out on my end and we can keep going. It is important to me, unlike your other classes, right? We're in the middle of a semester, which is coming to a close here for the colleges shortly. I believe Lake State has gone to virtual learning, although I have not heard anything about that. It is important to me that we continue because the reality is if you're taking this class in high school, you will be able to start as science majors in truly your sophomore year, not just in terms of credits, but also in terms of your prerequisites, which means that when you get to your first year of college, many of you will be enrolled probably in organic chemistry or analytical chemistry, and there are things that we need to talk about in general chemistry that your professors in those courses are going to expect you to already know. So if at all possible, I really do want to keep going and make sure that you guys earn credit for the course and even more importantly, have what you need to be successful when you move on from high school into the college and the universities. Um, so with that being said, we are still in chapter 15. We have one more topic to discuss, which is Le Chatelier's principle. Okay, so yes, that funky name there is pronounced Le Chatelier. It's not Les Chatliers, okay, French guy. This is in your text, section 15.9, which begins on page 703. I would highly recommend that in addition to watching this video, you take a few minutes and read through that section. It should be helpful to kind of help supplement this and again some more example problems and things like that to help you guys out. So Le Chatelier's principle is the idea that a system that is at equilibrium, if disturbed, will react in such a way to restore equilibrium. Alright, so what does all that mean? Let's take a look at a very simple reaction using what else, right? Legos. Right? So let's imagine for a second that we have this reaction. Okay, we've got RDYE in a decomposition reaction. Okay, producing some free RD. There's the red blocks there, and some free YE. There we go. And of course, we could write an equilibrium expression for this, right? Where K is equal to the concentration of RD times the concentration of YE divided by the concentration of RDYE, right, on the left side there. So let's imagine for a moment, and it happens to be that I have equal numbers of particles, but it doesn't necessarily have to be, right? But let's imagine for a moment that this system, as it sits right here, represents equilibrium. Okay, so both the forward and reverse reaction are happening in equal rates. Okay, and so right now we are at equilibrium. We have K. We could potentially do something to disturb equilibrium. For example, we could add to the left side of our reaction. Right? We could pile in some more RDYE. Okay? So what we've just done is we've increased the concentration of the RDYE, which now means we no longer have K, right? We have Q. And in this particular instance, Q is less than K. So in order to restore equilibrium, as Le Chatelier's principle would tell us, what has to happen is that this reaction now has to speed up in the forward direction. In doing so, it's going to generate some additional free RD and free YE, right? Some additional red and yellow. okay, in order to restore equilibrium. So we added some more RD, some more to the left side, and in order to correct that and restore equilibrium, the reaction, we would say, shifts to the right, okay, producing more red and yellow blocks. At the same time, we could do the exact opposite. We could potentially, to this reaction, add some more RD and some more YE, and again disturb equilibrium. Only now we've increased the concentrations of RD and YE such that Q is now greater than K. Well, now the reaction has to shift to the left. In other words, we have to form more more RDYE in order to restore equilibrium. So Le Chatelier's principle tells us that the reverse reaction will accelerate. Okay, it'll be greater than the forward reaction. Until we get back to K, right? Until we get back to that equilibrium value. So this is Le Chatelier's principle. You take a system that is in equilibrium, you create some kind of a disturbance. We'll talk about some other disturbances here in a moment. But you create some kind of a disturbance, an alteration to your system at equilibrium, and the reaction progresses in such a way to restore equilibrium. Okay? So let's take a look at that in terms of actual reactions. And we'll talk about some of the different ways that we can affect a system in equilibrium. Okay? So let's start with this. One of the first things and one of the easiest things that we can talk about is that we can change the amount. If we're talking about gases, we can affect the pressure. If we're talking about solutions, we can affect the concentration. So this is effectively what we did in our example with the red and yellow blocks. So here's an actual reaction. We've got N2O4 in equilibrium with NO2. And we could write an equilibrium expression for that where Kc is equal to the NO2 squared divided by the concentration of the N2O4. And so if we were to say add N2O4 to this side, well, that would increase this concentration, making Q less than Kc, and so the reaction would shift to the right. We'd have to produce more NO2 in order to compensate and restore equilibrium. Alternatively, if we were to increase the concentration of NO2 by adding more NO2 to this reaction, we would shift the equilibrium to the left, right? We'd get a Q value that was greater than K, and so we would have to push the reaction to the left, producing more N2O4 in order to restore the equilibrium. Okay? So that's kind of the simple example. Bear in mind, we could also take away things, right? So if we were to say, oh, I don't know, take away NO2, if we were to somehow remove NO2 as this reaction was happening, well, that would decrease the concentration of NO2, right? Which again would shift the reaction to the right. We'd have to produce more NO2 in order to restore equilibrium. Okay? So that's one example. We can change the amount. If we're talking about gases, we measure the amount often in pressure. If we're talking about solutions, or we could talk about gases in terms of concentration, but we could affect the concentration of a given solution. One of the other things we can do, if a system were to involve gases, okay, we could affect the volume. So let's take a look at this reaction. Oops. All right. So here's an example of a system that involves some different gases, and we could affect the volume. Think about a reaction taking place in a chamber of which we can adjust the volume. Okay, so think of maybe a syringe where you push the plunger in, you push that plunger in, and you reduce the volume. What we find is that for a reaction that involves gases, if you reduce the volume of the container that they are reacting in, again, presuming the system is already in equilibrium, the reaction will shift towards the side with fewer moles of gas. Okay, so in this example reaction, notice that on the left side of the reaction, we've got 4 moles of gas. That's 1 mole of N2 and 3 moles of hydrogen. On the right side, we've got 2 moles of NH3. So in this instance, we have fewer moles on the right side than we do on the left. So in this situation, if we were to reduce the volume of that chamber, okay, essentially push the plunger in on that syringe, we would find that the equilibrium would shift to the right. Okay, we'd end up with more NH3 once equilibrium was restored. If alternatively we were to make the chamber bigger, okay, we'd see a shift to the left. We'd actually shift towards the side with more moles of gas. Okay, so volume, okay, is another way that we can change or disturb a system that's already at equilibrium. The last one we need to talk about is the idea of temperature. Okay, we know that equilibrium can be affected by temperature, right? Because K is different at a given temperature. But let's take a look at an endothermic reaction. When thinking about how temperature affects equilibrium, it's helpful to think about heat as part of the left or the right side of the reaction. So in an endothermic reaction, that means that in order to progress forward, the left side has to absorb heat. And so you'll see here I've got heat written sort of like a reactant, right? Part of the left side of the reaction. So if we were to say increase the temperature of this system, we'd be adding heat. In other words, we'd be adding to the left side of this reaction. What that's going to do is it's going to shift the reaction to the right. Okay? We're going to end up producing more NO2. At the same time, if we were to cool down, okay, reduce the amount of heat, take away heat from the left side, what that would do is shift the reaction to the left. Right? We see something pretty similar in an exothermic reaction, okay, but in the opposite direction. So for an exothermic reaction, we can think of heat as being part of the right side, right? Heat is actually going to be reduced as this reaction progresses forward. And so if we were to increase the temperature of this reaction, we'd be adding heat. Well, if you add heat, you're adding to the right side of the reaction. To compensate, the reaction is going to shift left. At the same time, if you were to cool down this reaction, take away heat from the right side, right? You're removing something from this side, so now in order to compensate, the reaction has to shift to the right. Okay? So that's the idea of how temperature can affect equilibrium. Okay, so 3 main things. You can affect the amount in either pressure or concentration. You can affect the volume for a system that contains a gas, or you can affect the temperature. And depending on whether the reaction is exothermic or endothermic, it shifts the reaction one way or the other. Okay? There are some practice problems that I'd like you to take a look at that. You can go ahead and add those to the assignment that's already out there. I know that particular assignment's getting kind of lengthy, but I figure we've got time at this point. So take a look at those 5. You'll notice they're all odds, so you should be able to check your answers in the back of the book. In addition, I'm going to post a couple of additional worksheets. They kind of look more like quizzes. I think they're multiple choice, but they'll include answers as well. I'm going to try and do that for now because I don't know how else I'm going to be able to give you feedback. I'm not going to be able to look at your work, which is fine. So I'll just make sure that you guys have answers and you can kind of check yourself. And if you have questions, feel free to email me, and I can do my best to respond. If I get questions, I probably will respond on Classroom. That way everybody benefits if there's a question on a particular problem that we're looking at. In addition, I'm going to post a couple of slides talking about this same idea that I just covered, in case, I don't know, maybe the language is better on the slides, or I don't know. But if that helps, I'll post those as well. Um, so just an idea of where we're at. This is the last topic that we need to cover in chapter 15. Chapter 16 still deals with equilibrium, but we're looking at it in terms of acids and bases. And so we're going to start looking at that, I think, Friday. I'm going to give you a couple of days to kind of digest this Le Chatelier's idea, but I'll plan to post a video starting chapter 16 on Friday. We'll start by looking at strong acids and strong bases. And if you'll recall, we did some of that in Chem 2. We'll talk about how to calculate pH, and then we'll get into where it really matters in terms of equilibrium, which is weak acids and weak bases. So that'll be something completely new. Once we get through the chapter on acids and bases, which will include a short discussion on buffer systems, we've got one chapter left to cover, which is electrochem. So without having to do labs, because obviously we're not doing labs at this point, I expect that we'll be able to get through quite a bit here, and hopefully we're back on the 5th or the 6th or whatever it is. And if we manage to get through, even if we manage just to get through chapter 16, we'd only have electrochem and a couple of labs to do. So as long as we can keep up with the workload, I think we're still in pretty good shape to end sometime in early May. That's still my hope. Obviously it's a pretty tumultuous time. Nobody's really sure about anything at this point. But again, I want to make sure that we try and do everything I can to ensure that you guys get credit for the course, and that you have what you need for the next level. So I know it's been a lot of work, and you guys have worked really hard, so you deserve to be able to finish. And if we need to do that virtually so that I can submit grades, I'm okay with that. We'll make that happen. So, all right, guys. If you need anything, if you've got any questions or concerns or having issues, even if they're not necessarily chemistry related, I know there's a lot of anxiety about things right now, and I hope that it's not affecting you too much. But certainly, as the numbers seem to grow and whatnot, it can play on you. So, if there's anything I can do to help you out, please let me know. I'm happy to do that. So, all right, guys, stay safe, have a good night, and we will talk to you again soon.